Okay, I started the recording and just 1 second, can close this. Regarding exams, so let me open Alma Esami because I just published the dates of the exam. Just 1 second. And of course, when you log in, you get a different screen with respect to mine. So I put 3 dates. First, please remember I cannot make any exam before June 10. June 10 is a Saturday. And therefore, I wanted to avoid June 12 because some students among you told me that on June 12 there is another exam. Unfortunately, I think there will be many of such problems. So the 3 dates that I scheduled are June 13, 2023, July 3rd, July 17th. So the timing is 9 a.m. The place is the campus called Bertalia, which is in Via Terracini, number 28. And the place is a lab, a computer lab, which is called LADI, L-A-D-I, as you see written here on the screen. When we get close to the date, I will give you some information to the students who are subscribed on the logistic, like indications when you are at the main entrance of the building to get at the lab. In any case, there is already published in Alma Esami that if you need any indication of that type, you can go to the reception and ask them. But I will give you detailed information. Another thing, there are 150 places available for each exam date. I don't think it will be a problem because there is a max number of students, which is 200, as you know. And then you have to subtract some students who will decide not to give the exam for some reason. So I think 150 is usually the max number of exams that I make for this course every year. Good. So I don't think it will be a problem, 150, but just be advised that the system, after reaching the max number, will close to subscriptions. Subscriptions will open on May 2nd. As you know, you may decide to decline the mark. You can take all the 3 exams if you want. It's not a problem. And there is one thing that you should be aware of. In principle, the system allows you to subscribe to the 3 dates. But if you do that, if you decide, everybody of you decides to subscribe for all the 3 dates, there are 2 problems. First, the max number may be reached. I think this problem is unlikely. And therefore, the student number 151 cannot subscribe anymore. I don't think this will be a real problem. The second problem is that if you subscribe to the 3 of them, it is difficult to manage the logistic of the exam, not for me, but for you, because as you will see, I will need to split the students in groups. I cannot make the exam to more than 50 students at a time for logistical limitations. Therefore, if everybody subscribes to all the 3 dates, there will be some problems in the management of your day. This is why I would prefer that you make a wise selection of dates. And second thing, please, if you subscribe to the exam and you don't show up, this is a big problem. So avoid this. In case you don't show up, there might be the necessity for me to disallow you to take the exam the next date. Okay, because it is really needed that if you decide not to show up, that you unsubscribe. You are in time to unsubscribe until the closure of the subscriptions. Don't forget to do that, okay? Because you are many students, we have to get organized. So in a way, if you unsubscribe, you leave some room for other students and the management becomes more manageable. So there is no limitation. You can take all the 3 exams. So you know that this is something that it depends on it's my decision. So I'm willing to give the max flexibility, but if you are not careful in making the selection, and in particular, you are not careful in unsubscribing, I cannot offer the same flexibility. So keep this in mind. If you don't unsubscribe, there might be the impossibility the next round for you to attend the exam. I hope it's clear, but I will remind you, okay, because subscriptions open on May 2nd, so there is time. The last lecture, I will give you the final recommendations, and in my final recommendation, I will remind you. Last thing, the laboratory, I didn't find any lab with sufficient capacity for up to more than 100 PC, so I was forced to book this lab, which is also not in the center of the city, but this is not a problem. The problem is that the lab has only 50 places. So I will need to make the exam in rounds composed each time by 50 people. So if there are 150 students subscribed, I need to make 3 rounds, which means that I will have to split. First round 9 a.m., second round 11, third round 1 p.m., more or less. Okay, we will see. It depends also on the number of students, because I guess that you will not be 150, but you may be like 90. The first exam I am expecting like 90 students. So this is why I will need to split in 2 rounds. Of course, I cannot know this until the last student who unsubscribed. So I can give you the final timing only at the closure of the subscriptions. This is also why I'm telling you, please try to make a wise selection of the dates. I mean, the suggestion that I give to you is subscribe to the first if you want to try the first, and then if you decline for some reason, then you subscribe for the second. You don't run the risk, you don't have any risk not to find any place at the second exam, okay? It's impossible, and in case the impossibility materializes, we will find a solution, don't worry. So just try to manage your subscriptions in a wise way. Okay, and I will give you, of course, the details, who is in the first round, who is in the second round, when after the deadline for subscriptions, and we will manage, okay? Any question on this? Yeah, please, there is a question. Yes, but I will give you proper instructions. You will be allowed to get your login details online. And the second thing that I wanted to tell you, I prefer to give you the options to get the exam done on a PC that is shared by the university. For stability problem of the network, I prefer that you are working in the same conditions. But if you want to take the exam with your phone, your iPad or your PC, there is no limitation, it's up to you. Just keep in mind that in case there are problems, maybe a problem for you only. And therefore, I suggest that you take the exam on the PC of the lab, and if there is a problem, it's a problem for everybody, not for just one person, because it may be difficult to solve if it is for just one person. And you know, you have to rely on the stability of the Wi-Fi. In any case, I suggest you not to make the exam with the mobile phone. The iPad is fine, provided you check that the connection is good. I don't suggest you to make hotspot with your mobile phone and make the exam with your PC or iPad. The only problems I had with online exams were given by students using the hotspot in the rooms of the university, because the hotspot, you know, it's on average is less safe than the Wi-Fi, which is less safe than the cabled PC, the wired connection, which is definitely the safest. Everything is clear? And for the credentials, I will give you like a couple of days in advance. I have the emails of all the students. I will give you the credentials. Yeah, there was another question. Okay, sorry. Okay, good. If there are no other questions, I can start lecturing. Okay, let me close Al-Mazami then. Of course, if you have any problem with subscribing, just let me know. Finally, I just got communication that this course will not be repeated by the university the next year. So I think you will get communication on that. No problem for you. You can take your exam next year without any problem. I will continue to make exams until the last student has got it. The problem is for the students of the next year, which will not benefit from this course, and they will not benefit from any other soft skill course. The university decided to shut them up. So if you don't like this decision, like I don't like it, raise your voice. I you know, I don't understand why, but this was the decision, and of course I accept it. It's not my habit not to accept the decisions. Okay. Let me now close this window, yes, and let's go back to our climate models. And climate models, just 1 second, I need to, we got more or less, just 1 second, we got more or less here. And I finished my lecture by talking of heterogeneity and the grid. So I said these models need to be applied at the local scale. Let me just recap a little bit, and let me open the PowerPoint before I move forward, because I prefer to use the PowerPoint for lecturing. Okay. Let me just recap a little bit. We said that these models need to describe several processes, which are, some of them are highly heterogeneous. And heterogeneity means spatial variability. And therefore, this is why we apply the equations that build a climate model at the local scale, because we need to describe local specificity. We need to describe local conditions. And therefore, these equations need to be applied over a domain. The domain needs to be very local. Just to be clear, the equations which build physical models, and also in general equations that build chemical models, most of them are conservation equations, like conservation of mass, conservation of energy. For instance, if I want to describe the volume of water that flows into a river, I apply a conservation equation of the mass of water for the river, which means that given that the water is also flowing out of the river, I have a flow out of mass, I have a flow in because rainfall is feeding the river, and I have a storage. And I simply say that at any given time step, the inflow minus the outflow plus storage should equate to 0. So inflow minus outflow is provoking a change of storage. If you have more inflow than outflow, the storage decreases. If you have more outflow with respect to inflow, you have the storage that is, I have more outflow, the storage is decreasing. If I have more inflow, the storage is increasing. So this is an example of a conservation equation. This conservation equation is to be applied over a time step and over a spatial domain. The river is the spatial domain. And therefore, these conservation equations, if I want to describe a local feature like a river, need to be applied at the local scale. I cannot apply it at all rivers of the globe. If I apply it to all rivers of the globe, I describe the flow from all rivers, not from a single one. But what I need from a climate model is an estimation of climate change at a given location. It's not just enough for me to know how much global temperature will change. If I am only interested in the global temperature, I may apply the conservation equation over the whole globe. But then I get an indication of only the global change in temperature. Usually, I am also interested in knowing how much the temperature in Bologna will change at a certain time. And therefore, my conservation equation is to be applied at the local scale of Bologna. This is why I subdivide in grids. Of course, when I made the example of the river, I mentioned inflow and outflow because the river is connected with the flows to the other spheres. I said that the spheres of the Earth system are connected through flows. In order to apply these conservation equations, I need to take into account at any grid, any cell of the grid, I need to take into account inflow and outflow, which depend on the application of the model to the neighboring cells, application of the model to the neighbors. So you understand these equations are applied over millions of cells, and the solutions are linked. So I have to solve this equation at the same time. This is how we concluded the last lecture. I concluded by saying I need a lot of computational capability, a lot of computing power. So this is only possible for laboratories who can use a lot of computational facilities. It's not possible over personal computer, over this PC, to run a global model at fine scale. Of course, if I run a global model at the global level, it's possible. But if I want to describe millions of cells, I need these huge computers, supercomputers. Leonardo was just inaugurated in Bologna. The European Center for Forecasting has a supercomputer in Bologna, which was inaugurated 3 years ago. So these are the kind of resources that we need, especially if we want to really operate at the local level. So of course, if I am interested in a prediction over Europe, okay, the number of cells, it's not so large to cover the globe with cells with the dimension of Europe. With 10 cells, probably I can cover the globe. But of course, the prediction at the level of Europe, averaged over Europe, is not so detailed. Very often I need a prediction at the scale of 1 kilometer, because I need for some very small scale processes affected by climate change. Think, for instance, at urban heating in the cities. This is one problem caused by climate change. The heating in the cities is much higher than the global heating. the increase of temperature in cities, some of the cities in the world increase the temperature of 5 degrees. So this is something that is really, really important, really matters. And therefore, I need a description at the scale of this of a city, which means 1 kilometer. And if I need a description at the scale of 1 kilometer, I need supercomputers. Okay. Let's move forward. Now, we know already that we have to apply conservation equation. We know that this conservation equation can be conservation of mass or conservation of energy. These are the most used. And energy means that at the scale of any cell, I need to make a balance of the incoming energy and the energy that goes out from the cell. And incoming energy means many possible sources. At the global level, just keep in mind that the climate system is driven by solar energy, which is, if you consider the Earth system, it's the only energy income. Solar energy is the only energy income. So the Earth system is a closed system from the point of view of energy, and the only external source of energy is solar energy. So strictly speaking, it's not a closed system, if you want, but it gives, I think, a more understandable picture if we say that there are no energy exchanges, but the income of solar energy. At the level of the universe is a closed system. Okay? There is no income of external energy. But at the level of the Earth system, there is the income of the energy of the sun. We also already discussed it when we talked about energy fluxes. And of course, within the Earth system, there are several energy exchanges, and we have to know them, to take them into account in our models. Now, so Earth is heated by sun, okay, in an uneven way. Some part of the Earth receive more energy, and therefore there are differences in temperature. And this difference in temperature is compensated by the Earth system by transporting heat from the warm zones to the zones that are cooler. And in particular, there is part of the heat that is transported in the atmosphere from the equator to the poles. And the transportation of heat gives rise to ocean currents, wind, evaporation, precipitation, and global weather patterns. And these are the processes that we have to model. And again, these processes are driven by this disparity in energy that is coming from the sun. And so if we have, for instance, there are other disparities, like if you think of rainfall, rainfall that falls over the mountains has a potential energy when it reaches the ground that is higher with respect to rainfall falling over the flat areas. And so there is a disequilibrium of energy, which is compensated by river flow. River flow is an attempt of the Earth system to reduce this disequilibrium of energy. In general, you can think of the Earth system as something that tends to reach an equilibrium in terms of energy. And the equilibrium is given by the configuration that ensures that the energy is minimum. And in particular, for the water cycle, the energy is minimum when water is into the oceans at the same level. And if water gets at the same level all over the world, there is no more flow, because there is no need to reestablish equilibrium. It's already equilibrium. On the other hand, we always have, fortunately, water at different levels, and then we have this flow of water, which is, of course, useful for us and is impacted by climate change. Another example of how the Earth system tends to reach equilibrium. The fact that there are parts of the globe that are located at higher altitude is given by tectonic forces. So tectonic forces originated, the mountains are still originating the mountains. On the other hand, the Earth system reacts by trying to lower the mountains, to lower the altitude of the mountains through what? Through erosion. Why there is erosion? There is erosion because it's an attempt of the Earth system to reach a configuration of equilibrium. And therefore erosion is caused by rainfall that flows over the rivers, into the rivers and over the land. And this flow of water is triggering erosion, which tends to reestablish the perfect sphere. So all of these energy differences, energy disequilibrium, lack of equilibrium, means that these processes are kept in a dynamic phase and not in a static phase. Okay, and also you can think of the exchange of gases like carbon dioxide between the atmosphere and the ocean. It's also caused by a disequilibrium. So if you have an increase of CO2 into the atmosphere, CO2 concentration in the atmosphere that increases, there is a corresponding increase of CO2 dissolved into the oceans, which is also driven by temperature, by the temperature of the atmosphere and the ocean. Now, keep in mind that some, as I already said, some of these processes are not fully known. We still don't know how some of these processes really take place. I made the example, I think, already of the water cycle. It is something that is very trivial to understand it at the general level. It's very trivial. On the other hand, we don't have a full knowledge of the details of the water cycle. And there are some processes that we still don't understand how they take place. Even the very simple travel of a drop of water from the point where it lands on the ground to the river, we don't know how it takes place. Is it a superficial travel or it's a travel underground? Of course, we know that if we have a very impervious layer at the surface of the Earth, then we can we conclude that the travel is a superficial travel. It's a travel that takes place over the Earth's surface. But if we have a permeable layer, if the soil is permeable, we really don't know if the travel of water is over the land or under the land. It is something that it's still difficult to observe. Did you notice when there is a violent storm, if you are in a field covered by grass, did you see water flowing over the grass? Usually not. It may happen in some cases, but usually not. You don't see it. But after a while, the river floods. So this means that there is some traveling in the underground, but we don't know how much it's deep. We don't know many details. So how can we describe analytically something that we don't fully know? Of course, we have to make assumptions. Any model is based on assumptions. So we assume that the process, the dynamics, is governed by a certain equation. We assume that the energy losses, we have to account, if we want to make energy balance, we have to account for energy losses, but we can't measure them, and we don't know their magnitude. So we assume that the energy losses are described by a certain equation. Keep in mind that when I talk about conservation equation, it doesn't mean that there are no losses. It means that simply I take losses into account. So if I refer to a grid cell and I apply to a grid cell conservation of energy, Of course, there are energy losses. There is energy incoming and energy outgoing. It's an open system. A biological system in general, it's an open system, receives energy and gives back something, gives back some energy. Therefore, losses are fine. Losses are part of conservation equation. But these conservation equations, their dynamics, their intimate dynamics is in many cases unknown. And therefore, we have to rely on assumptions. Assumptions that we test then. Science needs assumptions. It is advisable, we all hope that we can test the assumptions. In some cases, it is not easy. Okay. In some cases, assumptions are tested by making an experiment. So for climate, the experiment is we run a model and we compare the model output with the observed climate. This is a test. But in some cases, we cannot make it. In some cases, when we talk about the description of the Earth system, we don't have enough data to test our models because you need the data at the local scale. I just said that the models have to be applied at the local scale. You need data at the local scale, and sometimes we don't have this data. But anyway, this is part of the scientific approach. We make assumptions. When we can, we test them. If we cannot test them, we have to be aware that there are approximations, which we hope to be able to evaluate in some way. Approximations means uncertainty. And once again, I tell you, uncertainty in principle is not a problem in science. It's maybe a problem in communication, as I said, and then we have to be aware of this. Okay. Now, I think I already mentioned to you the butterfly effect, which means chaos, which means chaotic behavior, and the butterfly effect is very entertaining, is very effective, and of course it is an exaggeration, like a flap of a butterfly in Japan may cause an hurricane in the United States. Of course, the butterfly doesn't create the energy for the hurricane. It just gives the start of it. It creates the condition for it. And why a butterfly effect may be so powerful? A butterfly flap may be so powerful because the flap of a butterfly, it's an initial condition. When you run a model that is based on the conservation equations, you need to specify the so-called initial conditions and the so-called boundary conditions. We don't want to get into the details of what they mean. I could easily give some more details, but I want to instead insist on the concept. The initial condition and the boundary condition, we can call them as the starting point of our model, the starting time, the starting point of our model. When I run a global model, I need, in a way, to start from a cell. And then I propagate the results all over the globe. But I need to start from a point. And then I try to make sure that all the solutions are consistent. But I need a start. I need a start. Even if it's a global model, I need a start. And at least I need a starting time because I cannot run a global model forever. A global model runs everywhere in space. So the starting point may be at the end of the story. It's a problem that I can in a way bypass because I try to apply it all over the globe. But I cannot bypass the problem of a starting time. I cannot run a model forever. So at the beginning, you have to specify what is the velocity of wind in Japan. And if the velocity of wind changes because a butterfly flaps, you have a different initial condition. you have a different starting point. The velocity of the wind is not 0, is 0.00001 because of the flap of the butterfly. Now, chaos implies that a small difference in the starting point translates into a big difference at the end of the simulation. This is chaos. Chaos means high sensitivity to the start of our model. The language that I'm using is very rough, but I hope that you can understand what I mean. The start in time or in space is effective because a small difference is making a difference in the final result. What does this mean? It means uncertainty, because of course we understand that it's not possible that the flap of a butterfly originates a hurricane into the United States. This is not possible. But given that the process is chaotic, it means that the model may give you a difference in the final result if you put the butterfly in Japan or if you neglect it. So what does this mean? It means that anytime that you listen somebody talking about chaos, also during your day-to-day life, what it means is something unpredictable. I mean, there is chaos. You use this word to say that the situation is very confused. You don't know what to do. There is chaos, we say, okay? And so anytime that you hear the word chaos, it means that making a prediction is difficult. And unfortunately, climate is chaotic. And chaos also means that even if we improved our monitoring systems, even if we improved our understanding of the processes, still chaos may be there. Because it is an inherent unpredictability, which is not related to lack of knowledge, is not related to the fact that we lack data. It is something inherent, you know, which cannot be bypassed. So you may ask, what is the solution then? The solution is maybe simply averaging. The way we deal with turbulence is by averaging, because this chaotic behavior, on average, they cancel each other. So averaging may be the solution. So averaging means that maybe that your grid cell cannot be refined so much, maybe that you cannot go to a precision of 1 centimeter in space because there is a lot of chaos. If you go to a higher scale, then what is the average movement of wind generated by a butterfly over a scale of 1 kilometer? It's 0. If you go to the scale of the butterfly, maybe that at 1 micron distance from the wing, then you have a big change in velocity of the air, and maybe that the air in the very small scale of 1 micron close to the wing, it's a big change in velocity. But then if you average, is 0. So chaos can be in a way overcome by averaging. And this is why when you listen when you hear of climatic predictions, you look at climatic predictions, they don't tell you on July 12 of 2050, we will have in Bologna 50 degrees Celsius. You don't get a similar prediction. You get a prediction like the average temperature over Italy in 2050 will be higher of 1 degree if the current pace of human emissions continues with the same rate. So they are averaging. They are averaging over the Bologna region, maybe they say that, or Italy. And they are averaging time, because they don't say, they say in 2050. They don't say on July 12. So this is why, in terms of climatic predictions, we talk of statistics. We are not very precise. We don't say in 2050 in Bologna, there will be a temperature that is 1 degree more. We say in 2050, from 2050 to 2100, over Italy, the increase in temperature will be like that. And keep in mind that when you talk about climate predictions, climate models, climate analysis, look at the spatial and temporal scale. If the scale is large enough, you get more confident. If the scale is very fine, for instance, we have models predicting daily rainfall in Bologna up to 2100. You have to know that this is a prediction that it's only valid if you take an average. It's not valid at the daily time scale. Any climatologist would say the same. Like, don't take the daily prediction in Bologna in 2050 day-to-day valid. You have to take it valid statistically, which means take an average. Okay? So beware of this, because when you look at prediction, and if you want to give to gain a scientific opinion, you have to look at the spatial and temporal scale. Another thing that you have to know is that when you look at a prediction, try to understand if the process is chaotic or not. Temperature is not much chaotic. Okay? You will never listen to somebody saying, if I increase of the temperature in Japan 0.01 degrees, I get an increase in the United States of 10 degrees. No, temperature is not chaotic. It is a kind of dynamic that doesn't suffer from chaos. What is chaotic is the movement of air. What is chaotic are all the processes that are governed by turbulence. So even water flow is chaotic at the very small scale. Okay. So if you look at a prediction of temperature, you have to be more confident in the prediction. If you look at prediction of daily rainfall, which is highly chaotic, you cannot be confident on the prediction. And I give you one more detail. If you look at prediction of rainfall during the winter, it's more reliable than rainfall during the summer. Why? Because rainfall during the winter, as you know, is given by rainfall that lasts for a long time. Like it is rainfall that is not very intensive, but lasts for maybe 1 month, 1 month of rain. Sometimes it happens that in February, it rains for all days with very, I mean, it's not a strong rain, but it is something long lasting. This process is caused by movement, by perturbation that have large scale, which are not very chaotic. During summer, rainfall is caused by storms which last for a few minutes and have a very limited spatial extension. Sometimes you go out, there is the sun, and in 5 minutes, you get completely wet under the rain. And if you move 100 meters, then people didn't experience any rain. What it means chaos, something that is difficult to predict. So predictions of summer rainfall are more complicated. Also for a meteorologist, they have more problems, more difficulties in predicting rainfall during summer than during winter, because they know that it's chaotic during summer. Thunderstorms are chaotic. There is a lot of research effort now dedicated to the simulation of convective processes in climate. Convective processes are chaotic because convection is chaotic. The summer storms are generated by convective processes. So we hope to move some step forward, but it is not easy. So when you have to assess a prediction, you have to derive information from a prediction. Beware of the uncertainties and try to gain your perception of the reliability of the prediction. You know that there is uncertainty, and your first question must be, how much is this reliable compared to other predictions, for instance? And then communication, again, is another thing. Okay. Now, this is what this slide says, and you see an example of turbulence in the picture, and which is turbulence caused by an airplane wing, which is visualized here with visualization techniques. And you see, it's there are changes at very small spatial scales. It's almost impossible to see them. Let me just check if I can. Okay, much better. Now, the purpose of modeling is not only to get a prediction, it's also an effort to understand. If a model works well, let's make this example. Let's suppose that you don't know how a system works, a determined system works, and then you make an assumption and you try to describe the system with an equation, but you don't know if the equation is a good approximation of the process. You test it, you see that the prediction is successful, and then the conclusion is that your assumption is solid. So it's also a learning process. And therefore, we have the prediction, which is one of the purposes of climate models, but there is also a lot of research in modeling for understanding. And this is extremely important. So sometimes I listen to people saying, okay, but these models don't provide the good predictions. So what is the matter here? The matter is understanding. I mean, if I see that a model improves, I still have some uncertainty, but it improves. It gives the direction to reduce uncertainty. It gives the direction of a better understanding. Now, from this introduction, I think you got that models can have different complexity. And indeed, the literature and also the data that you can download, the predictions, may come from models with different complexities. So, besides understanding the spatial scale, besides understanding the presence of chaos, another element that helps you to get an idea of the reliability of a model is indeed understanding the complexity, understanding if the model is a crude approximation of reality, which is still useful, or if the model is a very refined representation. The problem is not easy to solve because actually, and this is something that may be counterintuitive, if the complexity of a model is increased beyond our information availability, let me better explain. To run a model, you need information, you need data, okay? The more complex the model is, and the more data you need. So in order to run a complex model, you need a certain amount of data, which is commensurate, it's proportionate to the complexity. So if you increase the complexity, and the increase in complexity is compensated by additional information, uncertainty is reduced. If you increase complexity, but you don't have the additional information that is required by the model, then uncertainty may increase. So there is an optimal compromise between available information, which means data, available results from your experiment, and complexity of the model. So in order to understand uncertainty, it's not just enough that you look at the complexity of the model and you say, okay, this model is very complicated, it's very complex, so fine. The prediction is certainly more reliable than that of a simpler model. Actually, this is not the case. You have also to gain to understand if the model has enough information, which is, once again, directly related to its complexity. If the model doesn't have the required information from an operational point of view, from a technical point of view, in terms of reliability, it's much better that you make a step back and use a simpler model. because otherwise, as I said, and also take into account one thing. Okay, if we talk of modeling for understanding, every solution can be appropriate and justified, properly justified. If we talk about technical applications, and in many cases, this is our need. If we want to check if a mitigation action, like reduction of CO2 emissions in the future with respect to business as usual of 30%, this is a technical purpose. If you have a technical purpose to reach, it may be more appropriate a model that is not completely wrong with respect to a model which is in general better, but maybe in some cases completely wrong. So you may decide to use a model which is not very good, but not very wrong with respect to a model which could be much better, but also much worse. And in this case, the first solution, we talk about a robust model. A robust model is not really the best that you may have on the model market, but it's not very wrong under any circumstance, under any conditions. A model that is not robust may be very interesting because it may give you indeed a better description, a better prediction, but you have to be very careful in trusting it. This is all information that when you talk about science of climate change needs to be available to you. You may think that the picture that I am drawing is very complicated, like you need to know this, this, and this. Actually, it's not very complicated, believe to me. We are making a discussion that cannot require more than 3 hours to be completed. But if you start getting additional information, if you start to look at the model testing, there is a lot of information on model testing. If you go to the IPCC reports, there is a lot of information on models reliability. You will see that it's not so difficult to get this information. Of course, it takes time. If you read an IPCC report, it may take like 1 week to be read and for your purposes. But on the other hand, it's not a long time if you have to make, if you have to take an important decision. And the information is accessible. Okay, but of course, before getting the information, you have to gain awareness, and this is what I'm trying to deliver to you. And awareness means that, of course, I have to highlight the problems. I have to highlight what may be difficult to get, but on the other hand, I also want to be positive. The information is there. Science is working, and okay, so we may have simple models, and we may have complicated models. Let's move forward. Basically, this is something that I already discussed, heterogeneity, and I just want to say that the cells which compose the grid, they are three-dimensional. So it's not just enough to describe the land surface, which is described by, if I limit my description to the surface, it's just 2 dimensions. I also need the vertical dimension. I need to describe the underground. So these volumes, these are not cells, are volumes. These volumes are extended over the 3 dimensions of space. And of course, you don't need to go until the center of the Earth. These processes, you can at a certain depth stop them. And if you need to take into account fluxes of energy from the center of the Earth, you can do that. You can consider them like an external input to the volumes, to the infinitesimal volumes. But it's important to know that these are 3D models. You may find simplifications. You may find 2D models for the Earth system, or let's say for Earth system processes. So you may find in these models some of the processes that are described in 2 dimensions, which is possible. Okay. What is the spatial resolution of modern models, to give you an idea? So let's say that today, most of the models are working at a resolution that is between, if we talk about a cell over the land surface, the spatial resolution is between 5 kilometers of size of the square cells to 25 kilometers. And now most of the global models work at a resolution that is below 15 kilometers, which means in terms of square kilometers of land surface, it is, if the resolution is 25, is if the size of the square cell is 25 kilometers, then in terms of area is about 625 square kilometers. If the resolution is 10 kilometers, in terms of area of land, is the size is 100 square kilometers, to give you an idea. And I mentioned to you the convection permitting models. These are the last evolution of climate models. These may work at the resolution of 1 kilometer, which means 1 kilometer square. This is a very fine resolution. And they are still used for in the research context. For operational application, there is still a lot of uncertainty because they want to describe chaotic processes. But I just want to mention that people are working now on the resolution of 1 kilometer. I am working in a national project with within the National Recovery Plan, where I'm not in charge of this task, but one of the tasks is to try to provide climatic predictions at the scale of 1 kilometer. And the reason is precisely because we want to focus on urban areas also, because cities are really hotspots of climate change. And also people live in cities. And therefore, it is very relevant to be able to model what happens into the cities, because you know, we know that most of the human population is living in urban areas with different size. In big cities, there is a significant proportion of the human population that is living there. And so describing what happens into cities is extremely important. And there is still variability. There is still variability. Okay, so what are examples of quantities, matters that can be conserved in this conservation equation? It's energy, mass. I made these 2 examples so far, but there is also momentum. And don't worry, if you don't have familiarity with these quantities I'm mentioning, it's not a problem. Just, I think you are familiar with mass, whatever is your degree program, I think you are familiar with mass, and you are also familiar with energy. And we will have a lecture talking of energy. But there are additional physical quantities that are conserved, might be conserved when building these models. Momentum is a physical quantity, which is related to the velocity of the flow of this quantity flowing. And also water vapor can be conserved, and also the carbon can be conserved. We can write conservation equation for carbon in order to describe the carbon cycle. So basically at each grid cell, we have to describe these processes. They can change from cell to cell. In some cells, we may need to describe the river flow or water storage, and therefore conservation of water. If we go to the desert areas, conservation of water is less important, but exchanges of heat, of energy may be very important. So in some of the cells, we may decide to drop some conservation equations because they are not very significant and they don't play a significant role. So for the sake of simplicity, we may decide to change what conservation equations we apply here and there. But these equations have to be applied on every grid cell. Actually, this is not a big complication in mathematical terms because computers run through cycles. So it is very easy to apply the same equation here and here and here and here. From a computational point of view, it is easy. The problem is related more to the available information. So I may have a measurement of energy flux, energy income here, but not here. So we need to interpolate maybe the information that is needed in order to estimate the missing information. Okay. So basically, the purpose of these models is to describe these links between the spheres, to describe how energy and other matters like water propagate, travel, navigate the Earth system. This is their purpose. And Earth system means also oceans, means atmosphere. And so it's a very nice and exciting purpose. And as I said, we started a long time ago. And a long time ago, we had less information, less computational capacity, and which means coarser resolutions, and it means assumptions. It means more important assumptions. And then recently we try to increase in complexity. I just would like to, let me just give you an example. I move forward because I think at this stage I need an example. I am anticipating this slide. So as a very simple example of a model, of a climate model. So as I said, not necessarily these models are complicated. Let me give you a simple example which can be understood whatever your background is. And the simple example is considering the whole system as homogeneous entity. So only one volume. It's the volume of the Earth system encompassing the whole Earth system. And let's try to describe global temperature with an energy balance. This is possible. This is possible by considering with a simple equation, by considering the Earth system as a whole. And the equation is what you see on the screen. Let's try to understand how it is composed. So we have a quantity, capital S, on the left-hand side. I want to be very clear. So if you don't understand what I'm saying, please ask questions. We have a quantity, capital S, on the left-hand side, which is the solar constant. What is the solar constant? It's the incoming solar radiation per unit area. We know this is the incoming energy. We know this value. It's about, you see, 1,367 watt per square meter. Okay. This is something that we know. Okay. Now, A is the Earth average albedo, which is about 0.3. It means the albedo, it's something that governs the quantity of energy that is reflected back into the atmosphere and is absorbed by the Earth system. So by introducing the albedo, we can, in a way, compute the quantity of energy that is reflected back into the atmosphere. In fact, you see that if the albedo is 0, the overall energy is reflected into the atmosphere. If the albedo is 1, everything is absorbed, and therefore the atmosphere is not heated up. Okay, so now there is the pi, the constant pi, 3.14, etc. It's a constant, and R is the radius of the Earth, which is about, we know it, It's the value that you can see on the screen. And then the left-hand side is computed. And then we have the right-hand side, which is given by 4 pi r squared again, radius of the Earth, pi, we defined it. There is an effective emissivity of Earth, which is another parameter that quantifies the energy exchange between the Earth and the atmosphere. And then there is a constant, which is the Stefan Boltzmann constant. And then there is temperature. Okay, temperature, just 1 second, because I think here there is an exponent that is missing. Just let me check. Here it is. Yes. The exponents are missing. Let me check here. It's the 4, it's an exponent. Sorry for that. I realized it by looking at the slide. So the 4, the last 4 at the right-hand side is an exponent. I need to make a correction to the PowerPoint. Now, everything is known here, but temperature. So if we compute temperature from this equation, which is possible because the only unknown, I am expected to get an estimate of the average temperature of the atmosphere, which is given by this equation, which here you see that the exponent has been correctly taken into account, the exponent 4. And yields, such equation yields an average temperature of about 15 degrees centigrade, which is what we know. Now, let me go back here. How can we take climate change into account here? Better question. How can we take, what can change here? What can change? Not the radius of the Earth, not pi, not the Stefan Boltzmann constant. S may change. In fact, we know that if we have a change in solar radiation, we have a change in temperature. This is a big discussion, you know, natural variability. We know that may be caused by changes in solar radiation. Keep in mind that solar radiation is something that it includes some long-term cyclical variability, and long-term cyclical variability, which we know, the famous 11-year cycle of change in solar radiation. But in the past, we had also changes in the solar radiation that we still cannot explain. We cannot predict it. And there are several researches aiming to build a predictive model for solar radiation. This is important because, you know, it could compensate a little bit climate change, you know. And I think you may have also heard about geoengineering methods, studying possible solutions. They are not still not possible, but they are studying solutions for like building a screen that reduces the solar radiation over the parts of the Earth, the atmosphere that are more exposed, in order to compensate for climate change. These are geoengineering methods. We are not talking about them, but if you look on Google for geoengineering, you find a lot of references on these possible solutions. Another more consolidated solution is using coverages over the glaciers to save the snowpack, to save the glacier by covering them with white layers, white coverages that reflect back more solar radiation, so limiting the amount of energy that is absorbed by the glacier. These are widely used, only in ski resorts for now, but they may be used also for reaching the purpose of protecting glaciers in general. And of course, these are solutions that are a bit, critical for many reasons. Okay, but changes may be originated by us, and the changes may be included into the terms albedo and effective emissivity. The greenhouse gas effect is affecting, in particular, these two quantities, and therefore is causing climate change through changes in albedo and emissivity, and at the local level. So you see an example here of a model that is describing only temperature. So it's not describing all the climate. It's only temperature, and it's a model that is only describing an average temperature. It's not very detailed, but I think it's a good example to understand how this model works. Okay, let's okay. Now, if the models become more complex, you need more inputs. What are the inputs? The inputs are, in this case, the solar radiation. And there are some parameters. Let me go again here. Sorry for that. Sorry for jumping back and forth. The input here is S, and there are some parameters. And parameters here are sigma, the albedo, are the Stefan Boltzmann constant, which is a parameter that is indeed constant, is not affected by climate change. And parameters are epsilon, reflectivity, and the albedo sigma. And the albedo A, sorry for that. Parameters means that these are coefficients that usually take a constant value, but under change, they may change their value. Okay, and in particular, as I said, the Stefan Boltzmann constant is not affected by climate change, but the albedo and epsilon, the emissivity, they may be affected. Here we have only one output, which is temperature. Temperature is, as I said, the unknown. So in a model, you can identify input data, input information, output information, and you can identify parameters. Parameters that, in general, they may be known forever, like the Stefan Boltzmann constant, or in the case of albedo or emissivity, they may need to be estimated. If the complexity increases, I'm going back to the previous slide. If the complexity increases, the input requirement, the information requirements increase as well. I already mentioned this. And they may be, this input information may be observed or may be predicted as well. Like the solar radiation, we are making an effort, as I said, to predict it. Another relevant driving force, which I would classify as an input information, is the concentration of carbon, the concentration of CO2 in the atmosphere, which needs to be predicted, because for the future we don't know it. It is, I said concentration of CO2, but I should better say concentration of greenhouse gases, which is not only CO2. There is also methane, there is aerosol, and other gases. So this information, as I said, needs to be predicted. And let me talk about predictions of CO2 concentration in the atmosphere. What we need to know to elaborate a prediction of CO2 concentration for the future is the amount of CO2 emissions from humans, because these are influencing the CO2 concentration in the atmosphere in a significant way. And these predictions of CO2 concentration for the future are depending on our socio-economical development, and also they depend on the management of this socio-economical development. So, for instance, if we decided to rely on renewable energy as we are doing now, of course, the CO2 emissions in the future by humans would decrease a lot. Because as we will see in another lecture, most of the CO2 emissions by human, the majority of them are related to energy production. Burning of fossil fuels, we know that, okay? And burning of fossil fuels for various reasons, maybe for mobility, but maybe also for farming, for heating buildings, for cooling buildings. There might be several uses. But I mean, most of it is related to, for instance, as I said, electricity production. And of course, the management that we decide to make into the future of our development is important on that. And therefore, in order to make predictions, we rely on assumptions. Like there is the business as usual scenario, which is also called in technical terms RCP. We will see why RCP 0.5. The business as usual scenario, which is called RCP 0.5, assumes that we continue to increase our CO2 emissions like we did in the past. So the increasing trend of human emission is continuing into the future. It is called RCP. The acronym derives from Representative Concentration Pathway, RCP, which means representative pathway of release of human CO2, human-derived, human-produced CO2. There are other assumptions, assuming that we break our current increasing trend in the release of CO2 emissions. We already acted towards to reach this purpose. So it is reasonable indeed to assume that the rate of increase of CO2 emission will not be the same in the future as it was in the past. In fact, there are several scientific sources highlighting that the business as usual, the RCP 0.5, is a too pessimistic scenario for the future. Of course, maybe that our purpose of reaching by 2050 the carbon neutrality is too optimistic. On the other hand, we really hope that there are significant steps forward in order to decrease our increasing rate of CO2 emissions. But the concentration pathway is extremely important. And let me just show you some graph. Let me see, RCP Wikipedia. RCP climate, better. Let's look at this figure. It is very recent, and therefore I didn't include it in my web page. I don't think it is included. Let me check. Maybe that it's already there, or I check later. Okay, so let me check now. Here there is something actually, but let's look at this figure first. So here you see the first, you see the different RCP from 2000 to 2100, and this is the CO2 equivalent in part per million. This is the concentration of CO2 in part per million in the atmosphere. And you see the different scenarios. The most optimistic is the RCP 2.6, which means that we stabilize the concentration of CO2 in the atmosphere after 2040. Now we are more or less at this level, 400 part per million. So there is this prediction that we stabilize about at around about 2040, and then we go down in the future. And then there are the other scenarios, RCP 4.5 and RCP 6, and then there is the pessimistic RCP 0.5. Okay, actually, this picture is taken by the 5th assessment report of the IPCC, and now the 6th report is being released. So this is why you see here that the divergence between the scenario starts around 2010. The 5th assessment report is dated 2013. And therefore 2013, 2015, I don't remember, around that time. So they already diverge the scenarios at 2020. Now the last scenarios, they start from 2020, and the divergence starts from 2020, because of course we have to get the same value for all the scenarios at the present time. Okay, so this is an example, and here there is a more detailed description. If you are interested, I'm not going into more details here. If you are interested, just look at how these are computed. Just keep into account that this is a very important decision that you have to take when taking a decision in order to mitigate climate change, adapt to climate change. An important decision is what is the scenario, the emission scenario I refer to. And now, as I said, there is a lot of, here there are more scenarios than those that are shown in the figure that I just projected on the screen. And now, here you see RCP 0.5, emissions continue to rise through the 21st century. Since AR5, this has been thought to be very unlikely, but still possible, as feedbacks are not well understood. This means that we cannot really predict how much the CO2 concentration will continue to increase even after we stop releasing it, because of the inertia in the system, which depends on the feedbacks. And here you see the prediction of global warming for the different scenarios. There is a significant difference, as you see, from 3.7. Look at between parentheses, 2.6 to 4.8. This is the uncertainty range. Okay, so RCP 0.5, 3.7 by 2100. If you go to RCP 4.5, which is not unreasonable, it's not overly optimistic, it's half of it. Okay, and so I mean it's a relevant decision to be taken. What is the emission scenario I refer to? And now let me go to my web page, and here you see this graph is dated. The historical observations are up to 2020, as you see, more or less. Maybe it's 2019. And here you see that there are the observations, historical, and then the scenario that were drawn starting from around 2010, drawn for the 5th assessment report. And you see the different scenarios here. There are many of them. You see different acronyms because in the previous assessment report of the IPCC, they used a different indicator of CO2 emissions, and therefore they changed their acronym. Now they think of resulting concentration in the atmosphere. They quantify the human emission. They make a picture of the human emission by referring to the final result of CO2 concentration, because it looks like there is less uncertainty if we look at the state of the atmosphere after the emission, instead of looking at the emissions, at the global amount of emissions. It's better to refer to the resulting CO2 concentration. Okay, and this graph is taken by carbonbrief.org. And let me click on the link because it is an interesting website. And it is, in particular, this blog post is dedicated to the next generation of climate models explained. It's an interesting reading, by the way. But there are several blog posts on Carbon Brief that are several information that is very useful if you want to increase your knowledge of climate problems. And the nice feature of Carbon Brief is that everything you find there is public domain. This is, unless it is differently specified, this is a very nice feature. So this is why I'm referring to Carbon Brief often for my lectures. Keep in mind that when you want to get, and then we make the break, when you want to get information about climate, you know that climate change is to some extent controversial. So there are basically two extremal type of information which you may find. And there is the information that is delivered by the IPCC, like, let's say, IPCC is not a good example for this, but there are two extremal sources of information. One is the so-called information of the climate skeptics. I'm not saying climate deniers. This is an unscientific term. Let's call it climate skeptics. And there is the opposite side, which is the information that comes from the scientists that are more convinced that climate change is human-induced. When we talk about skepticism, it's not about climate change. As I said, there is nobody that is questioning that climate is changing. It is the attribution that is a question. It is controversial. I already mentioned this to you. And so you have these different sources of information. And the skeptic type of information is more reduced for several reasons, but it is also not prevailing. As you know, the great majority of science is converging on the idea that most of the climate change is human-induced. As I said, nobody questions the human influence on climate, but there are some part of science, some scientists questioning its significance with respect to the natural variability. This is the very scientific question. But the part of science and scientists who is convinced about the human significance is much larger, as you know. On the other hand, in science, we shouldn't talk about consensus, but only about different interpretations. And therefore, it is important, if you want to get an overall picture, that you get the information from both sides. Of course, reliable information, because on both sides, you can find some information that is unreliable and some information that is more reliable. So you have to be selective, because especially on the skeptic side of it, you may find interpretations that are not very reliable. And this is also on the other side. But on the other side, given that the information is more extended, it is, by chance, more difficult to pick up an unreliable information. But what I want to say is that if you want to get an informed opinion, a scientific-based opinion, you have also to ensure the diversity of your information. You have to make sure that your information is diverse. You cannot get even if an information is representing the minority of scientifically valid opinions, you have to be informed about it. And then you gain your interpretation. And this is the right way to follow, okay? So what I made this long premise to say that Carbon Brief is shifted towards the IPCC side, the side of the prevailing science, which means that it's you have more chance that the information delivered by this group and by Carbon Brief is solid. For sure, the information delivered by Carbon Brief is solid. And but on the other hand, tendentially, usually, I don't suggest any information from the other side. I prefer not, because it's more difficult to find reliable information on the other side. But I stimulate your curiosity, get informed, because I think it is important, okay? And I tell you, I did it. I'm continuously reading scientific papers of climate skeptics, continuously, because I really want to get the point from both sides. I really want to get the point. And if you want to get the point, you have to listen to a diversity of interpretations, like in politics. But in science is different, because politics is talking about, of course, strategies and interpretations. In science, we should be talking about facts, about evidence. But of course, also in science, sometimes you need interpretations, because when you don't understand something, you have to deliver, you have to make an assumption, and an assumption is also an interpretation. Okay, I'm a bit late with the break, and let's take 15 minutes break, and then let's meet again at 4:40. And then I will close at 5 at the given time, 5:15.
Scusi, però posso farle una domanda al volo?
Sì, prego.
Solamente logistica. Gliel'avevo chiesta anche alla lezione precedente. Per i laureandi di luglio, lei fa un appello prima della scadenza dei requisiti del 28 giugno?
Okay, the question is, for the people that have to degree in July, is there an exam by the deadline of June 28? Then I translate in Italian. Yes, of course. If you attended the first part of the lecture, the first exam is June 13. 13 giugno il primo appello.
Yeah, but it's the only one for June, not an extraordinary, let's say, extra appello.
Guardi, io praticamente non posso fare esami dal 24 in poi, quindi non so che senso abbia fare 2 esami nel giro di una settimana. Cioè, di fatto, quello è in tempo utile. Io però non posso fare esami il 28, cioè andare oltre il 22 non riesco, e se io faccio 2 esami in 10 giorni, dopo non è una distribuzione di date che non trova concordi gli studenti degli anni successivi, in sostanza. Ma non capisco perché un esame solo non le basta. Perché...
No, io lo studierò al meglio, ma metti che magari non vada con un voto adeguato, uno magari aveva una possibilità in più. Ma vabbè, nessun problema, e grazie comunque per la disponibilità.
Comunque, in ogni caso, se poi quando siamo lì ci sono delle urgenze, le possiamo vedere assieme, d'accordo?
Va bene, grazie mille, prof. Grazie.
In generale tenga presente che fare 2 appelli d'esame a distanza di una settimana non ha molto senso, nel senso che non è che in una settimana lei riesca a migliorare la sua preparazione in modo significativo. L'altra cosa che deve tenere presente è che è molto difficile in un esame come questo non passarlo. Chiaramente, cioè, voglio dire, non è che lei non si laurea se non corre questo rischio, secondo me.
No, certo, anzi, al contrario, ho una media elevata e volevo proprio per questo prendere un bel voto. Era per questo che dicevo, magari lo rifaccio se c'è qualche sbavatura da voto basso. Comunque lo studierò al meglio, poi eventualmente ci risentiamo. Grazie mille, prof.
Prego.
Grazie.
Okay, let me pass to the web pages because I need more details now. Let me see. Here we are. Okay. Now, a key feature then for a model is the time and spatial scale, as we said. In terms of time step, we need to distinguish between the time step at which simulations are produced and the computational time step. They might be different because there is a lower limit at the time step simulations are produced, which is dictated by the need to minimize the effect of chaos. As I said, there might be a convenience to refer to average values over time. For instance, when we look at the time resolution, the time resolution is the time scale at which simulations are given. For rainfall, there is a lower limit nowadays at the daily time scale, which is already perhaps too fine in order to provide a simulation that is not affected by chaos. But the computational time step may need to be lower than that, because the computational time step is the time step that each model simulation is updated. The time step each model simulation is run. And the numerical error, the error of the numerical simulation, which is an uncertainty that is introduced by the fact that simplified numerical schemes are used. This kind of numerical error increases or increasing length of the time step. So it's a different type of error. It's not an error due to the presence, not only to the presence of chaos. It is an error that is given by the fact that, as I said, the mathematical equations, their numerical simulation involves a computational error. So in order to reduce the computational error, we need to minimize the time step. So it may go down to a length of 30 minutes, as you see on this slide. Typically, this time step of 30 minutes may have been used also by some models of the previous generation. This doesn't mean that the output is given every 30 minutes. It means that the output is still given at the daily time step, but the computation is repeated every 30 minutes. So just be aware of the fact that the computational time scale is not corresponding to the time resolution of the model. Okay. I think here everything is already discussed, has been already discussed previously. Yeah, there is another thing, the last bullet point, I need to make a comment on that. Is there a way to decrease the spatial and temporal resolution of models? So in order to improve the local description? Yes, there is a way, and the way may be to improve the model, by improving the description of the Earth system processes. We discussed this already. There is a second way, which is called post-processing. And you may get some information on that. You may listen about bias correction, uncertainty correction, post-processing, statistical downscaling. This is a post-processing of the model results, which is usually done with models that are completely different from the climate models. And basically, they are often statistical models, as simple as, in some cases, as bias correction. What does this mean? It means that if I get a prediction for the current temperature in Bologna, which is overestimated by 2 degrees, because typically in temperature we have the case of overestimation. So I simulate with the climate model the temperature in Bologna for the past 20 years, and I see that it's overestimated with respect to observation of 2 degrees. Then I downscale the future prediction by 2 degrees. So I just shift the average to be the same as that has been observed in the historical period. If the model predicts an increase with respect to the average of 1 degree, this is preserved. Okay, it's just as simple as an adjustment of some statistics. And this is, as I said, called very often bias correction or statistical downscaling. It's a kind of post-processing. Post-processing is the usual technique in engineering, post-processes of prediction, and also in physics. It means that we recognize that the predictions, there are some uncertainties that we can quantify and we can correct. It's a kind of correction. Good. Now, the example here, we have already seen it, and there is an extended set of examples of models that are given by the so-called CMIP project, is the Coupled Model Intercomparison Project. This project is a project that is currently comparing different climate models in order to identify their strengths and weaknesses. And there are a lot of these models that are proposed, data are given, and in particular now the project is focusing on the last generation of climate models that supported the assessment report 6 of the IPCC. How can you find these data? I think I already mentioned to you that dealing with these databases, these public databases of climatic prediction is not easy. Let's say that some programming skills are required for retrieving the data. I just want to mention you a couple of links which you may consider if you are interested. And I think the best thing is to look directly on the web. And CMIP project climate. You see the climate, the Wikipedia page of the project here. 1 second. And here you see all the phases. The last one is the 6th one. And there is a website presenting this simulation from the 6th phase. And in order to find it, you have to go to the, let me go again in Wikipedia, in the Copernicus data store. The climate data store by Copernicus. Copernicus is the European agency that takes care of storing the climate data with the particular reference to Europe, but you can find also data at the global level here. And here, basically, you see that there is a description of the information that you can find, data sets. There are a lot of data here, and they are not only climatic data. There are also data referred to the Earth system, which are related to hydrology, related to biology. There are a lot of variables because, as I mentioned to you, the climate models now are being extended to generate more than just weather, more than just climate. And in particular, they are being extended to generate also river flow, assessment of water resources, etc. And in order to download these data sets, as I said, which also include observations. This data, climate data store also includes observations. You have to go to this toolbox, and there are a lot of documents that explain to you how to retrieve the data. And in this toolbox, we need to run, unfortunately, a code in Python. For those of you that are expert of computer programming, with a code in Python, you can you need to write a code in Python to download the data. There are several examples. So I'm not an expert of Python. I could manage, and here, in particular, the code has to be included here. You first need to register, but the registration is free. So you have to create a new account here. And then there is full access to the console, which allows you to download the data through a code in Python. But as I said, there are some examples. So it is being improved. It's becoming more user-friendly, but still it's a bit of demanding in order to manage the data retrieval. This is just to provide you an overview on a toolbox that allows indeed to download an extended set of very fine resolution data. Related to Italy and related to more statistics than data, you may have a look at the CMCC website, CMCC Foundation. And here they also provide climate maps for Italy, which show what are the predictions of climate change for Italy given by different models. And you have to navigate the website. I never accessed this data. While I accessed the data on the Copernicus data store, I never experienced. There is also the English version of the website. Now I opened let me see, the Italian one. It's not here. So let's see. Anyway, there is the English version, which is here. Sorry. Okay, you see here, and if you look at the website, I'm sure that there are the maps from Italy. Here there are reports on climate risks. There is a lot of information. The CMCC is really well organized. They also offer summer schools, schools for students, which you may find interesting. And you may also attend one of these summer schools. In general, you can attend a summer school instead of getting an internship. If you have an internship in your study plan, you may apply for recognizing the summer school as an internship. And these summer schools are very well organized and really very informative. Okay. Here there is a description in the next slides of the RCP, an extended one, and we already discussed it. Let's talk now about uncertainty a little bit more. I already mentioned the importance of uncertainty, but let's try to make a more structured discussion. So what is what are the reasons for uncertainty? We can, climate modelers, usually classify uncertainty according to the categories that you can see in the bullet points in the bottom of the slide. There is an uncertainty related to forcing. And let me make an example. CO2 emissions. Of course, the predictions for the future, the scenarios may be not reliable. There is an uncertainty which is related to the model. So what does this mean? It means that even if the forcings were correctly specified with no uncertainty, even if we neglect the inherent uncertainty due to chaos, so even if we were able to give perfect initial conditions, there is still a residual uncertainty which is due to the fact that the model is not perfect. This type of uncertainty, in principle, could be eliminated in the future. It could be eliminated because had we reached in the future a perfect understanding, a perfect description of the Earth system, then model uncertainty would become negligible. And then there is the uncertainty of the initial conditions and boundary conditions, which we already discussed, which is something that is difficult to eliminate because, you know, we will never be able to provide a description, a detailed description of turbulence at the very fine, at the microscopic time scale. It's impossible. Okay. It is important to get an understanding of how these types of uncertainty combine in order also to be able to deliver an effective communication. So understanding uncertainty is also important because if we understand it, we can explain it in an effective way. Because again, the presence of uncertainty doesn't mean that the model is useless. It doesn't mean that the prediction is unreliable. It may mean that the prediction is reliable in statistical terms rather than in point terms, rather than at the very local, spatial, and time scale. But it is still very important. In order to understand what we need to do to face climate change, we don't need a very detailed description to the point in time, to the point in space. A statistical representation with uncertainty, it's just enough. It's not a big problem. It's not really a big problem. Okay, so model uncertainty, I already discussed it, and initial conditions. Now, let me spend a few words on testing of climate models. Usually, this is a highly debated topic. How climate models can be tested. And the usual way in Earth system sciences to test a model is to try to reproduce data that have been observed and to make a comparison. For instance, in hydrology, this is a usual procedure. In water resources, it's a usual procedure. We make a prediction of river flow, of water scarcity, and we test the prediction with observations. So if I want to build a model for describing the river flow of the Po River in 2050, my first step is to test the model against observations of the river flow in the Po River from 1920 to today. This is an essential step. With climate models, this step is a bit delicate because actually climate models, if you make some testing, are not successful. So climate model cannot reproduce the climate of the past at the very detailed scale. They can only reproduce the statistics. And the reason is that given their sensitivity to initial conditions, it's a very high sensitivity. And given that for the past, we cannot specify these initial conditions with precision because we cannot reconstruct the initial conditions starting from 1850, it turns out that the prediction of the past, where there is a lot of chaos, is not reliable. The post prediction of the past it's not reliable. It's reliable in terms of statistics. As I said, if I want to average out the effect of chaos, I need to refer to averages. So I cannot really look to make a comparison for the climate models in Bologna of the observed rainfall in 2020 and the simulated rainfall in 2020, because they don't match. This has been the subject of criticism. On the other hand, the statistical comparison is possible. I can make a comparison of the average rainfall in Bologna from 1990 to 2020 and the simulated value. This is possible. And this is the way testing should be done. It's a kind of statistical testing, but it is also the subject of relevant concerns because, you know, other branches of Earth system sciences, as I said, they are testing at the very local level. In principle, they can do that because there is less sensitivity to chaos. On the other hand, it's clear that if you have a model that is only reliable in a statistical way, it gets less confidence from the end user. So there is a lot of debate on how the model should be tested, how the results should be presented, because, you know, last week I went to a meeting with the stakeholders for drought predictions, and at the end of the story, I presented without mentioning uncertainty. At the end of the story, one of the stakeholders said, okay, but these predictions are only valid in a statistical sense. And he said that with a negative connotation, with a negative tone. Like, okay, your prediction is fine, but it's only valid in statistical terms, which means that you are not sure of it. And so this is why it is the subject of a strong debate, and we need to explain how climate models are tested, because otherwise there is an increasing lack of confidence by the end users on the output. Let me say that I think science has its part of responsibility in that, because, I mean, when we issue a prediction with a lot of alarmism, we have to expect this type of reaction. I think that climate science, in some cases, has used too much alarmism. I spoke with climate scientists about this, and their reply is, if we don't predict a disaster, then we don't get the attention of the stakeholders, of the policymakers, of the politicians. I understand the point. On the other hand, there is to say that if we make a prediction, like it was done in the past, that by 2020 climate would change a lot, and then nothing happened, what you have to expect is a lack of confidence in science with respect to climate. And I listened to, and I participated to a discussion with some climate scientists that aimed to present some, some predictions for 2030. And again, sorry, one of them said, it's too early, we cannot take the risk. I fully agreed with him. If you make a negative prediction for 2030, which is in 7 years from now, and it doesn't come true, this is a big problem. And we shouldn't take this risk. Given that it's possible, I mean, it's possible that the prediction doesn't come true, especially if it's overly pessimistic. So I think science has its own responsibility, but it is clear that there is a decrease of confidence of the public and the politicians and the stakeholders in climate predictions. Keep into account that climate actions have, as I said many times, a high social cost, and so they are demanding. So it's clear that people, when they are directly called to pay the cost, they try to downgrade the prediction. This is clear. I give you an example. In Florence, some years ago, they issued a flood map showing which part of the city would be flooded if another event like the flood in Florence in 1966 occurred again. Keep in mind that the hydrologic conditions are unchanged. So if another meteorological condition like 1966 comes, then Florence is flooded. So they issued this map, and the map lasted for about a couple of weeks because the owners of the houses that were shown to be flooded, they asked for the map to be withdrawn, and they had to withdraw it because you know, it is a social cost. If you show that an area is prone to a risk, there is a high social cost in it. And the people that are called to pay for it in first person, even if you promise a kind of support of, they get really reluctant. So again, uncertainty is to be correctly presented and we need to be aware of it. Just to give you an idea, these are the predictions given by 3 models for the trends of global temperature from 2 models actually, from 1900 to 2000 to 2000. And you see that both models in the reconstruction with respect to the observations, they have differences, discrepancies, especially in some periods. And in particular, if you look at the period of the global cooling, which took place from 1950 to 1980, more or less, you see a lot of discrepancy because probably the global cooling, which I think we already discussed, was caused by forcings that are not taken into account by climate models. And this is probably the reason of the discrepancies. But just to give you an idea, you see that the difference is something like 0.2 or 0.3 degrees between simulation of different models. It's a significant difference. When we are talking about a warming of 1 degree, if you have 20% error, 30% error in the temperature, which is a variable that is easy to be predicted, you know, it's an important difference. So what we do in order to minimize this uncertainty, to first estimate it and then to minimize it, is to make what are called ensemble predictions. We use different models or different initial conditions for the same model, and we generate several simulations. And by looking at the envelope of the different simulations, we get an idea of the uncertainty that may be induced by the initial conditions, of the uncertainty that may be induced by model uncertainty, because if we use different models, you look at the envelope, we get an idea. And this is the way uncertainty is today quantified for climate models. But still, this may miss important contributions, like if all the models are wrong, they give maybe similar predictions, which means that you may overestimate model uncertainty because you see that the differences between models are low, and therefore you may think that model uncertainty is low. But if all the models are wrong, then the difference with respect to observations may be much larger than the width of the resulting envelope. A common approach is to look at the ensemble average. So we take the average of different simulations to compute the best prediction. This is a wise idea. It has the problem that it lowers variability, because of course, if you get an average between different models, you tend to get a flat picture, because you have some models overestimating the future temperature, some models underestimating it. And if you take the average, it doesn't necessarily converge to a best prediction. What you obtain is a lowering of the variability. But still, computing the average may be a good idea, but not only one. We may get the worst model, the more pessimistic one. But in doing that, we run the risk of significantly overestimating the impact. And if you overestimate the impact of climate change, you overestimate also the social cost, which is a bit of a big problem It's really a big problem, okay? Because if the social cost is overestimated, then you decrease once again the trust of people in the climatic predictions. So uncertainty assessment for climate models is still an open problem. The scientific community is working on it. And you have to be aware of that for your assessment. And then again, once again, in communication, you may decide whether to mention it or not. Last week, when I had my meeting, I didn't mention it. Okay, ensemble is discussed here. And so I think this is fine. And here it is discussed the problem that I just mentioned. So model structural uncertainty is only partially accounted for by ensemble prediction. But you have to be aware of what an ensemble of prediction is. This is today the usual way climate models are run. To give an idea, this is global warming projections, a picture. This is from AR5. Different models, you see that they estimate the global warming at a given scenario. It is the previous SRES scenario A2, which is, I think, if I well remember, the business as usual. And you see that there is a lot of discrepancy between models. And this is something that also in the past, they just converge on the current observation because they have been constrained to do that, to reproduce correctly the observation at the current time. It was 2010, AR5 was 2010, and assessment report 5. And you see that there is a lot of spread in the prediction, even if you look at the lower one, it's +2 with respect to the long-term average. So it's anyway an important indication, but also if you look at the spread, it's a spread that is quite significant. Okay, I would just 1 second, I see how many slides are, yeah, only one. Okay, just 1 minute for this slide. This is an alternative to climate models. It's not very popular. It is the usual procedure that was applied in the past prior to climate models to generate future prediction. It is a statistical method. And it's a statistical method which is based on the analysis of climate observations, and they basically extend to the future the current trend of change. This method is criticized. The use of this method today is criticized because there is a prevailing movement towards climate models, not statistical models, but models that are based on conservation equations, etc., that are based on digital twins, on a numerical reproduction of the real functioning of the Earth system, which is fine. On the other hand, I recently made a study where I have shown that in some cases, the use of the old method provides more pessimistic predictions with respect to climate models. Because, you know, the two methods have different uncertainties. And so, in this case, the question arises, what is the best one? It's the more pessimistic that is generated by the old method, or it's the more optimistic prediction of climate models in view of their uncertainty. So my conclusion in this study is, let's combine the two. Let's consider in the ensemble also the old approach. And then I think we can conclude this overview of climate models with, I conclude with this mention of the old method. I mean, changes, we tried to predict changes in Earth system processes already before the introduction of climate models. And now we are progressing with a more detailed and comprehensive knowledge. So I hope this overview gives to you the idea of the mathematical methods that we can use for elaborating our predictions. Do you have any question? Thank you. See you next Monday. Tutto bene? Chiedo
Sì.
all'interprete.
Sì, sì, tutto bene, tutto bene.